All right, let's get on to relative motion. This can be a little bit confusing, but once it's broken down into its components, it's actually much more straightforward and easier than the problems usually first look. So humans in general are very good at analyzing relative motion. When we try to catch a moving object, position, velocity, acceleration of the object all have to be accounted for, and we just do that automatically. We've watched so many things move because we've spent so much time on Earth, all of our time on Earth. We're very, very comfortable with acceleration of objects due to gravity, so we're very good at predicting projectile motion. And then we're also very good at predicting the motion of other objects while we're also moving. But how do we actually calculate this? For example, if we wanted to determine the flight path for an aircraft that is landing on a moving aircraft carrier, the aircraft speed and velocity is given relative to the air, and the aircraft carrier is moving relative to the water. How would you actually calculate if those are the values that you knew? How would you calculate the velocity of the aircraft or dictate the velocity of the aircraft with respect to the aircraft carrier? So equations or problems can get quite complex, but we can break them down to make them a little bit easier. So when we have relative motion, what we mean is the motion of one object with respect to another object. So we can relate both of these with respect to some fixed point, but we want to relate them sometimes with a moving point because maybe our reference from where we're viewing the motion of some object or calculating motion is actually moving itself. So we can define, same as before, the absolute positions of two particles A and B with respect to a fixed reference frame. So RA and RB are going to be our absolute positions. And they are with respect to a fixed reference frame. So we have our position vector RA here, and that's going from our fixed observer to our translating observer, or our observer that's moving, observer 1 or object 1. And then we have RB, which is our position vector from our fixed observer to our object at point B. So our translating observer now is located at point A, and that person or that object is also moving. And so we can describe the relative position vector of the translating observer with respect to particle B as RB/A. So we can define the vector that is RB/A is the position of B relative to A. And if we think of these just as vector quantities, which they are, we can add them just like vectors, and we can get RB is just equal to the vector sum of RA plus RB with respect to A. So we're just adding RA and RB/A. And then likewise, if we want to rearrange, sometimes we might want to solve for that relative motion. We can rearrange this so we can get RB relative velocity or position of B with respect to A is just equal to RB minus RA. So if, for example, we have RA is equal to 4I plus 5J, meters, and RB is equal to 10I plus 2J meters. Just picking arbitrary vectors. So vectors are just our x and y components multiplied by their direction vectors, and then our RBA, our relative position of B with respect to A.
There we go. Okay.
So our relative position of B with respect to A would just be equal to RB minus RA. So we would take vector B, subtract vector A, we would end up with 6I minus 3J. So that's position. If we want to find acceleration, acceleration is very much the same as it has been before. We're going to find the relative velocities by taking the time derivative of the relative position equation. So velocity is d dt of r b slash a, which is equal to the velocity of b with respect to a, which is the velocity of b minus the velocity of a. And if we were to reverse this, maybe we wanted to find the velocity of a with respect to b. It's the same thing with position vectors as well. We could say the velocity of a with respect to b is actually just the negative of this. So that would be velocity a now minus velocity b. So velocity of b with respect to a is just the negative of velocity a with respect to b. And negative, I mean the vector is pointing in the opposite direction. So acceleration, take the time derivative of the relative velocity equation. So we have dv b slash a dt. So that would be our acceleration of b with respect to a, and that would be acceleration of b minus acceleration of a. So if we can find our position and their velocities or accelerations, whatever we're looking for, in vector form, it becomes quite easy to determine what our relative velocities and accelerations are, because we are just adding and subtracting those fixed coordinate or absolute vectors. Absolute just means with respect to some fixed space, something that's not moving with respect to time. So typically it would be with respect to the ground. So with respect to B, A with respect to B means A is fixed or B is fixed. A with respect to B means the velocity of A as viewed from point B. So whenever you see these subscripts, these are the relative velocities. So they're not with respect to some fixed point. They're with respect to a moving point. And that would be the second half. So the top one over here is B with respect to A. This is A with respect to B. And this is B again with respect to A. So the relative velocity just means if I'm traveling in a car and see my buddy over there also driving in a car at a different velocity, maybe a different direction, how fast does it look like they're going as viewed by me, because I'm also moving? So if you have two cars going in the same direction and one of them is going faster than the other, but they're both moving forward, the faster car would see the slower car as if it was moving backwards, relatively, because it's passing it. So that's all that these equations are showing. So if we're going to solve problems that have relative motion, which is a concern, we typically need to find the equations as vector equations. And once you have them in vector form, you can solve them in one of two ways. If you have them in vectors and they're equations written in Cartesian vectors, you can just add or subtract the components and solve for any unknowns. Or you can draw those vectors and solve the problem graphically using trigonometry. And then usually you have to use or make use of the laws of sines and cosines to actually solve those problems. So if you choose to solve things graphically, I've just summarized the law of sines and law of cosines here for a triangle with side lengths lowercase ABC, and then the interior angles capital ABC. This is just our sine law and cos law. So you can use these to solve problems if you choose. I prefer just using the vector method because a lot of times we're given velocity or acceleration, especially in terms of its components, and we can calculate velocity and acceleration in terms of the components, and it doesn't matter what coordinate system we use. So we can get a vector form for velocity and acceleration, and then we can find our relative velocities. So let's do an example. Two planes, A and B, are traveling with a constant velocity as shown. So the plane A is moving towards the right at 650 kilometers per hour, and plane B is moving 800 kilometers per hour downwards to the left, and it's at an angle of 60 degrees with respect to the direction of motion of plane A. Determine the magnitude and direction of the velocity of plane B relative to plane A. So we want to find the relative velocity, magnitude and direction of the velocity of plane B relative to plane A. So to do that, we need to find VB with respect to A, and we know that's going to be equal to the velocity of B minus the velocity of A. And then once we have this as a vector quantity, we can calculate what is the angle and the magnitude. So let's show the vector method. So if we choose our coordinate system, let's say this is X, and let's choose this as Y, then we will get our velocity of A. We write this in vector form would be 650 times I, and that's in units of kilometers per hour. The velocity of B would be equal to what? What is the absolute velocity?
Negative 400 I and then negative 693 J.
Yeah. So we'll just take it a few steps slower. So it's the X component is going to be 800 cosine 60. And that's negative because it's pointing the component in the X direction is going to be in the negative X direction that we've drawn. So negative 800 times cosine of 60. And that's in the I direction. And the Y direction is also negative. It's going to be negative 800 sine of 60 times J. And we can rewrite this as negative 400I minus 693 J kilometers per hour. So we have the velocities of A and velocities of B. So now if we calculate VB with respect to VA, which is just the vector VB minus VA, we would get negative 1050 I minus 693 J kilometers per hour. So if that is our vector, how do we find now the speed and the direction? So we have our vector.
You just like sum the components using the Pythagorean theorem thing.
Yeah. So this isn't to scale, but let's say this is our vector. So x, y, and we have our I component is negative 1050. And this is negative 693. And let's say we want to express our direction with respect to the horizontal. So this is our theta that we want to find. So this total distance here in the middle would be v. We want to find v and theta. We know v is going to be equal to the square root of the component squared. 1050 squared plus 693 squared. So that'll be equal to 1258. And then if we recognize that this angle here is the same as this angle, then we can write our equation tan theta is equal to 693 divided by 1050. And if we inverse tan of that ratio, then we get in degrees, our angle is 33.4 degrees. And we would write that like this. So this symbol here just shows that the arrow direction is the direction of our velocity vector, and that's with respect to the horizontal. So then this would be our answer for our magnitude and our direction.
Sir, regarding tests and midterms, for the final answer, would you want it in 3 sig figs? So like for example, 1,258 kilometers per hour could be 1.26 times 10 to the power of 3.
Yeah, so the way that Brightspace works for that, I can do significant figures, but it's somewhat of a headache. So what I'll do for my questions is I will tell you what to round to. So for a question like this, I would say, what is the magnitude of the velocity of plane B with respect to plane A? Round your answer to the nearest kilometer per hour. I would say something like that. Or for the direction, I would say round your angle in degrees to the first decimal. So that would tell you how much to round your answer and in what units to give it in, just to eliminate any of the issues. And then we'll look at as well. But just to try and make actually, I don't want to test your ability to type in a number to a computer. All right, we got time for one more example. So this question's a little different. At the instance shown, we have car A and car B. They're traveling at velocities of 40 meters per second and 30 meters per second respectively. If A is increasing its speed at 4 meters per second squared, whereas the speed of B is decreasing at 3 meters per second squared, determine the velocity and acceleration of B with respect to A. And it says the radius of curvature at B is rho B is 200 meters. So rho b is 200 meters. So where would we begin? First, write down what we want to find. We want to find the velocity of b with respect to a and the acceleration of b with respect to a. So we know that these equations are just equal to the subtraction of the absolute velocities and absolute accelerations. So let's find equations for the absolute velocities to start for each of those vehicles. So velocity b, let's choose our coordinate system to be like this. So x is to the right and y is upwards. What is our velocity of car b, or absolute velocity?
$30 meters per second.
Not quite. So we've drawn our x coordinates. We want to write them for our absolute is going to be with respect to our coordinate directions. And we can choose coordinate directions whatever we want. I just chose them along the direction that the car A is moving. So car B is not moving along either x or y. So it's going to be the sine and cosine components of the velocity, whichever one corresponds to our x and y directions. So for velocity b, our x component of velocity is going to be -30 because it's moving in the negative x direction. If we zoom in here, we have the x component. Let's draw this a different color. VBX, and in this direction we have VBY. And we know the angle inside there between the velocity and our y direction is 30 degrees, so we can write our x direction is equal to -30 times the sine of the angle, sine 30. And that's our I direction, plus our y direction is positive because it's driving upwards, so plus 30 times cosine 30. And that would be our j direction. And if we calculated that, we would get -15 I plus 25.98, so let's just say 26 j meters per second. So velocity at A is pretty straightforward. It's just traveling along the y-axis, so we don't have any x component. We just have 40 j meters per second. So if we have our velocity, our absolute velocities b and a, we can find now vb with respect to a, so it's our absolute velocity of b minus our absolute velocity of a. And I'll just write that as equal to minus 15I minus 14j meters per second. And if we calculated the magnitude, we would get 20.5 meters per second. And our direction, we would find it as 43.1 degrees, and that would be downwards from the horizontal. So I just skipped through the velocity section because I want to have time to cover the acceleration part. So for acceleration, how would we write our acceleration of the car? What we would do is we could break it down into each of its components. Since we have a particle or a car moving along a curved path, we know the speed and we know the radius of curvature, it seems pretty logical that we might use a normal and tangent components of our acceleration to get our acceleration vector. So we can write our total acceleration of car B would be equal to the tangent component of B plus the normal component of B. So the tangent component is going to be going along that path, and the normal component is going to be pointing inwards from that path. So what is the tangent component? Let's go back up to the question. It says car B is decreasing its speed at 3 meters per second squared. So decreasing its speed, that means the tangent component is going to be -3, and the component of that vector that is acting in the x direction is equal to sine 30. And because the tangent vector is actually in the negative direction, let me draw this the other way. Because it's decreasing its speed, let's just draw it this way. So this is actually a positive value. So plus 3 sine 30, and that's I. And then we have -3 cos 30 j. So that would be our tangent acceleration. And we have to add our normal acceleration. So our normal acceleration is our speed squared divided by our radius of curvature. So for our first component, we would have -30, which is our speed squared, over 200, our radius of curvature, times cosine of 30 would give us our x component, minus 300 or 30 squared over 200 times sine 30 times j would give us our j component. So finally, our acceleration of b would be equal to -2.397 I minus 4.848 j meters per second squared. So that's the vector form of our acceleration of b. The vector form of our acceleration of a, it said a is increasing its speed at 4 meters per second squared, and that's in the positive direction. So a is much easier. That's just equal to 4j meters per second squared. And so we can finally write our relative acceleration AB with respect to A is equal to the absolute acceleration of B minus the absolute acceleration of A, which would just be equal to -2.397 I minus 8.848 J, and that's in the units of meters per second squared. And if we wanted to find the magnitude by the same process as before, our magnitude would be 9.17 meters per second squared. And our angle because we use theta for velocity, let's use phi here. Our angle phi would just be equal to 74.8. And that would be downwards from the horizontal in this direction. So that's degrees. So the difficult part is finding, for acceleration, is finding the actual absolute values. Once we have those in vector form, it's quite easy. Just subtract the vectors to get our relative values, and then the same process we did for our velocity, we can find the magnitude and the direction. So I went a minute over time, but we'll finish up just in time for a short quote. Today's quote is, "Kind words do not cost much, yet they accomplish much." So thanks for joining, and I'll see you guys tomorrow.
Thank you, Professor.